All right, so thanks. It's great to be here. And it's great to be at a conference celebrating Rick. So this is joint work with Rick. And I'm also Rick's postdoc. So I guess when I first started learning about the dimer model, I was reading like lectures on dimers by Rick. And as I learn more and more about the dimer model, you learn more and more things, and more of them revolve around Rick and all of the amazing things that he's been able to understand. And all of the connections that have come from understanding the dimer model and combinatorics, probability, complex analysis, and geometry that are also really reflected in all the people here. So it's an incredible subject. It's been really great to work with Rick, and I'm excited to tell you about this as well. So happy birthday, Rick. And so I'll tell you what this model is in a minute. I'll just start with some motivation, and feel free to ask questions at any time in the middle of the talk. Okay, so what is sort of the context? So the context that I think a lot of people here know, is that for dimers in the plane, you have this sort of theory of limit shapes. So if you look at random dimer covers in 2 dimensions, you can look at sort of the corresponding height functions that go up or down by 1 as you follow a domino, depending on the color. Or up or down by 1 or 3 as you cross a domino. And in this sort of scaling limit, as you look at larger and larger graphs approximating the same region, these things sort of concentrate on a particular limit shape configuration. And they concentrate on this particular limit shape configuration, and because the 2D dimer model is exactly solvable, and you can actually compute things like partition functions and their asymptotics, this limit shape thing that you get is also something that can be explicitly computed. So you can actually compute what this limiting shape is, and it has a lot of structure. It has these sort of facets where you see one color. It has this liquid region in the middle. There's a sort of algebraic curve, which is their interface. And all of this stuff is sort of computable in part because the dimer model is exactly solvable. So in 3 dimensions, we sort of with Scott and Nishant, we sort of learned that there's sort of also a limit shape story for dimers in higher dimensions. So if you look at random dimer tilings of Z3, they also converge to some limit shape. And there's some things that are sort of different in how you set this up. There's no height function, so there's this limit shape, instead of being like a function corresponding to this tiling, is a vector field corresponding to this tiling that I'll talk about a bit later. But we really can't say much or really anything about what these limit shapes actually look like. We just know they exist. And that's in part because the dimer model in higher dimensions is not exactly solvable. So you can't compute partition functions. There's no formula. So this limit shape is the unique minimizer of some functional, but we have no formula for that functional. We don't know what it actually is. So this is sort of, I guess, some motivational setup. What I'm actually going to talk about today is sort of a limit shape theory for this other model, which is kind of a variant of the dimer model, and which you can very heuristically think about as some kind of large n limit of the dimer model. So we call this the multinomial dimer model. And in just a second, I will tell you what this is, but it comes with a parameter n. So for any n, you have this some multinomial measures on the dimer model that we call multinomial dimer measures. And you can look at what happens in this limit as you take n to infinity. And it turns out that this model is actually exactly solvable in the large n limit, even if you don't have a planar graph. So if you're looking at graphs in 3 dimensions, 4 dimensions, it doesn't matter. You can actually compute asymptotics of the partition functions as n goes to infinity, and then you can derive things like the surface tension. So that's what I'm going to tell you about today, is basically the limit shape theory for this multinomial version of the dimer model. So here's an example, which is with height functions, just to get things started. So here's the height function for the Aztec diamond limit shape. So I showed you the dimer pictures a few slides back. This is a graph of the height function, where the region where you see all the color, the liquid region in the middle, is sort of this green part, and the facets where it becomes linear are these white parts. And here's the sort of multinomial dimer limit shape in the large n limit. And this thing is actually smooth everywhere, and it has a very simple explicit formula. It's basically x squared minus y squared up to a change of coordinates. So if you drew this with different x and y, it'd be x squared minus y squared. So there will also be a version of this in higher dimensions where we don't have a height function, but I just want to start with an example. Okay, so let me tell you about what the model actually is. So for the standard dimer model, we're just looking at perfect matchings of graphs. That means some collection of edges where every vertex is covered exactly once. You can do this on planar graphs. You can do this on non-planar graphs. And sort of a natural way to put a probability measure on these things is to just pick a bunch of edge weights. So it's just a bunch of, for me, these are just going to be positive real numbers. And look at the sort of Boltzmann measures on dimer covers where the probability of your tiling is proportional to the product of the edge weights. So we're going to use this in order to define the multinomial version of the model. So we have this additional construction. This is where we kind of build the dependence on n. Is we start with some initial graph. So just because it's slightly hard to draw these pictures, my initial graph is just an interval with 4 vertices and 3 edges. And for every vertex, you blow it up by replacing it by some number of lifts. So here are by nv lifted vertices. And then you replace every edge with just all the possible pairwise connections of the lifts. So in this example, here I have 3, 4, 4, 3 as my choices. And for most of my talk, these are going to be constant, so they would all be the same. But I just wanted to give a slightly more general example. So here I have 3 lifts of the first vertex and then 4 lifts of the next vertex. And then every lift here is connected to every lift of its neighbor, and so on. So this is some auxiliary graph that you can build from your original graph G. So if I did this with not just a line segment, then I would have some big gnarly mess on top of some other more complicated graph. And the inverse of this is just that you project back down. So sort of what we're going to look at are dimer covers of this blow-up graph. So if you fix these ends and you look at a dimer cover of the blow-up graph, then we can kind of project it back down to something that is like an n dimer cover of the original graph. So an n dimer cover of the original graph is you pick these nv's, and an n dimer cover of the graph is one where you have a collection of edges such that with multiplicity, so that each vertex is covered nv times. So for me, realistically, n is going to be constant. N won't vary with v in this talk really. But you can do this when n is also varying. And the way that we're going to put a probability measure on these n dimer covers uses this blow-up graph. So we just look at, what we do is that we choose edge weights on the original graph, and then we look at the probability measure on dimer tilings with those weights, so that if this is an edge E, then all of the lifts of E get the same weight, WE. And then the probability of a dimer cover is just the weights to the multiplicity of that edge. So this gives us sort of on the upstairs blow-up graph. This is just one of the Boltzmann measures on dimer covers that I said on a previous slide. But when you project it down, it sort of matters how many ways there are to lift your sort of downstairs configuration to an upstairs configuration. So let me do a quick example, and then I'll see if there are more questions about the definition. So here's an example. All the edge weights are 1. Your graph is just the square, and n is 2 at all the vertices. So there are 3 possible 2 dimer covers of the square. They're given here. So you can either have 2 parallel vertical, 2 parallel horizontal, or you can have multiplicity on 1 on all the edges. So let's see what the probability of each of these configurations are for this multinomial thing. So what we have to do to determine that is see how many ways there are to lift each of these tilings to a tiling of the blow-up graph. So let's start with this one. So here's my picture of here's a picture of the blow-up graph where I've drawn some dimer tiling of the blow-up graph. So for one of these ones where you have 2 and 2, on an edge that has a 2, you either pick the 2 lifts that are crossing or the 2 lifts that are straight. So that means that you have 2 choices for each edge, so there are 4 total lifts. On the other hand, for this one, where you have multiplicity of 1 on every edge, for the first, when you lift the first edge, you have 4 options. Let's say maybe I choose this one. So then this vertex is occupied, but you still have 2 options for the next edge. And again, you'll pick some vertex to be occupied here, so maybe I take this one, then this one is free, and so again there are 2 options And then at the last one, there's only one option. But so this one actually has a lot more lifts. It has 16 lifts. And so what this is sort of saying is that with respect to this multinomial measure, this configuration where all the multiplicities are 1 is actually a lot more likely than the configuration where where you have two pairs of 2. So this is very different from looking at uniform measure on the set of these sort of downstairs n-dimer covers, because it kind of prefers things to be spread out, basically. That's how I would heuristically think about it. So any questions about the definition of the model before I talk about other aspects of it? Okay, so to get to where I'm going, let me tell you about what ultimately we're sort of interested in what happens in sort of a scaling limit. That's where we see this sort of limit shape phenomenon for regular dimers. But now we have this additional parameter n. And first we should just talk about what happens when you take what happens in the large n limit just on a fixed graph. So this model, where does this model come from? This model was introduced by Rick and Cohn a few years ago in 2021. And this is what they studied. They studied basically what happens if you fix a finite graph and just look at what does this model look like in the large n limit on a fixed finite graph. So first, what are sort of the partition functions for this model? Well, they're just you just sum over all the dimer tilings of the blow-up graph, the weight of the configuration. And the thing that kind of makes basically the sort of solvability of this model comes from the fact that these partition functions form a generating series. So if you sum over, so here when I write boldface n, I mean, so boldface n factorial means the product over v of nv factorial. And boldface x to the boldface n means xv to the nv product over v. So this thing is just a polynomial. And yeah, so this sort of packaging of them as a generating series you can use to sort of extract asymptotics. And at this point, we've assumed nothing about the graph G. So this sort of solvability of this model comes from the fact that you can kind of you can expand using this sort of generating series structure as n goes to infinity, and not from sort of determinants, which is sort of more classically where the solvability for the 2D dimer model comes from. So just to sort of emphasize a bit that this is kind of a different type of solvability. I wanted to say something about the Castellan determinant formula and sort of when it's possible to find Castellan weights. So yeah, so for regular planar dimers, you can compute the partition function using determinants. And what do you need to know about your graph for this to work? Well, basically a necessary and sufficient condition is that your graph doesn't contain K33 as a minor. So here's K33. And here's just a random picture showing you that you can fit K33 as a minor, i.e. all the vertices are embedded as vertices and edges are embedded as edges or concatenations of edges, using not that much space in the non-planar subgraph of Z3. And it also really doesn't work in these blow-up graphs because as soon as the multiplicity is at least 3, you contain K33 in one of these blow-up graphs. So this is just a way of saying that determinants are an extremely powerful tool for planar dimers. This sort of large N expansion is also a way that you can sort of try to derive formulas, but it's a very different type from the determinant formulas. So I just want to emphasize that they're kind of separate. Okay, so to say a little bit more about what you can see in large N. So if you are on a fixed finite graph and you sort of fix, you have these multiplicities NV and you sort of fix how they're going to infinity relative to each other, then there's this sort of important object called the critical gauge, which is just a function on the vertices which solves this equation. It's basically saying if you sum over only the vertices incident to a particular vertex u, the product of this thing on all the edges incident to u, then that is sort of proportional to, it's alpha v proportional to its contribution to the sum of these weights over all the edges of the graph, which is what this polynomial p is. And if you have a bipartite graph, which is our setting here, then this sort of splits this x change of gauge function splits into two functions, one on the white vertices and one on the black vertices. And it splits just because all the neighbors of white vertices are black, all the black neighbors of black vertices are white. So each of these equations is sort of telling you about one or the other function. And these functions are sort of unique up to scaling one by a constant and the other by 1 over a constant. So their product is actually unique. And so something that Rick and Cosman showed is that if you look at the large n limit on a fixed finite graph with these edge weights and that you fix the multiplicities to go to infinity in this way, then basically there's some function on the edges, which is sort of the limiting multiplicity of the edge. And that will concentrate on these critical edge weights given by the solution of this equation. So in some sense, these critical edge weights are sort of the object that's kind of capturing the large n behavior on a fixed finite graph. So before we try to take more complicated scaling limits. So let's do an example. Let's do the Aztec diamond. The weights are all 1. Then somewhat miraculously, the critical gauge has this very simple formula in terms of binomial coefficients. And so you can check the gauge equations with all of the with these weights plugged in and so on, and then if you take products of these, then the critical edge weights are just simple rational functions depending on n. So here's n equals I think 5. And these are just, each edge is labeled with the critical weight. So it's actually a little surprising and weirdly special that these have such a simple formula. In general, we actually don't know, we know very few examples. I'll show you one more example in this talk in 3D, but we know very few examples where the critical gauge functions turn out to be rational. And we don't really know what it is about the graph that causes this to happen.
Similar stuff for any size of the Aztec diamond?
Yeah. So the n here is this distance.
Oh, okay.
Or yeah, I guess n is 4 actually. Yeah. So n is 4, and then I in this picture, and then I and j are just are coordinates that tell you which point you're at. It's slightly funny because there's sort of coordinates for the white vertices and coordinates for the black vertices. So you have to choose a labeling.
And is alpha equal to 1 here?
Yes, alpha is 1. Alpha is 1, and the weights are all 1. Okay, yeah. So it's in this case we have it's sort of surprising, but you have these rational weights. This was in Rick and Cosman's paper from 2021. But it's sort of not known. It's not known more generally when there's rational critical gauge. But there is actually an algorithm to compute these things numerically. So I'll show some pictures with some numerical calculations later. But I also wanted to just give you a sort of simpler form of the critical gauge functions. So you can sort of scale things so that if you take all the edge weights to be 1 and all the multiplicities are the same, then the critical gauge equations just look like this. It's just telling you that the sum, if you take the product of f and g at the endpoints, then their sum at any vertex is 1. Okay? And so in particular, you can kind of just turn finding the critical edge weights, so these products, into a linear algebra problem. So you take a matrix, which is the bipartite adjacency matrix of your graph. So the rows are indexed by the white vertices and the columns are indexed by the black vertices. And each entry is 1 if there's an edge between those two things and 0 otherwise. And solving these critical gauge, finding f and g to solve these critical gauge equations is equivalent to finding just diagonal matrices that make this product of matrices bistochastic, which just means that for any row or any column, the sum is 1. And then if you find this sort of conjugate matrix, which is bistochastic, then its entries are the critical edge weights. So there's a Markov chain to do this, which is just that you basically, you say, okay, I want to satisfy, this is using the graph as bipartite, but you say, okay, I want to satisfy the critical gauge equations at the white vertices, at the white vertices, so I multiply by this matrix and make that happen. And then you say, okay, after I've done the replacement of all the values to make that happen, I will do a replacement at the black vertices, and so on. And you can iterate this to get a solution numerically to these critical gauge equations. So they are sort of computable, but numerically and not exactly. Okay, so in order to move towards sort of getting a more general sort of global limit shape story, we have to actually take scaling limits of these graphs. So we have to take sort of sequences of larger and larger graphs. So I'll just explain sort of how we set up to do that. So the first thing is to sort of fix a lattice. So I'm only going to talk about very regular lattices, so you can just think of ZD for this whole talk. But in general, you can take the white vertices to be a copy of ZD, and the black vertices to be ZD plus some translation. And I'm going to make sort of a simplifying assumption that all of the edge, if you look at the sort of edge directions in the lattice, that if you look at any white vertex, they all have the same set of incident edge directions, and I'm going to call those vectors E1 up to ED. So for example, for Z2, you could draw these as your 4 edge directions. But I'm allowing for there to be more complicated things, but it just has to be such that at every white vertex, the collection of edge directions is the same. And I'll explain why I'm putting this definition here later, but there's something called this sort of polytope, which is just the convex hull of the edge directions, which will play some role later, so I'm just mentioning it here. For more general lattices that are more complicated than ones where all the incident edges are just, all the edges incident to a white vertex might be different, then you'd have a more complicated definition for the Newton polytope. But it's simple here because the lattices are simple. And so sort of the setup for our problem is that we're going to take some compact region in RD that has some reasonable region, not some insane fractal, and we're going to approximate it by a sequence of regions in this lattice where the lattice spacing is getting smaller and smaller. And the heuristic and not well-defined question that we want to answer is sort of what do these n dimer covers of these graphs Rn, if you sample them from these multinomial measures, what do they look like in the iterated limit as you first take this multiplicity n to infinity, and then you take the size of the graph to infinity? So sort of to make this a well-defined question, we need a way to actually compare dimer covers to say what look like means. And we want to do this in a way that makes sense in any dimension. So in 2 dimensions, and I guess I showed these pictures earlier, you can compare dimer covers with their height functions. But this is a sort of special for the dimer model, this is something unique to 2 dimensions. So instead, what we're going to do, and this works in any dimension, is we're going to compare them using what I'm going to call discrete flows, which I'll just explain what they are. And I'll explain later that this gives you kind of the same, this is in 2 dimensions is sort of equivalent to thinking about the gradient of the height function. So it's sort of the same thing in 2 dimensions, but generalized to higher dimensions. So what is a discrete flow? So let's say we have some n dimer cover of a graph, and I'm just going to use m sub e to denote the multiplicity of the edge e in m. Then there's a corresponding discrete flow, which is just a function on the edges that is just where I rescale it in capital N. And so when you rescale it in capital N, oh yeah, I forgot to say that I'm assuming that the multiplicity at this point is constant n at all the vertices. It's not varying anymore. But when you divide by n, it takes values that are multiples of 1 over n. We sort of view this as a function on the oriented edges. This isn't a super important comment, but if you sort of reverse the direction of the edge, you reverse the sign of this thing. And the sort of important thing about this structure is first it gives us some way to compare dimer tilings, where we're sort of viewing each dimer as sort of not just the edge, but sort of the vector corresponding to the edge. And these things have this sort of rigid constraint, whether n is 1 or whether n is anything, that if you look at sort of the divergences, so you sum over all the edges, orient it out of your vertex v, this function, you'll get, it just depends on the parity. So it will be +1 if it's a white vertex and -1 if it's a black vertex. So these things, they determine the tiling because they determine m sub e, and they make sense for any capital N and in any dimension. So the way that we're going to sort of compare dimer tilings is by comparing what their corresponding vector fields look like. So a way that you can think about this is that you can kind of look at like basically the slope per white vertex, which I'm defining by saying that, so originally we had this setup that there's some collection of edges incident to any white vertex. And what I do is, if this is my vertex V, I just add up the values of this sort of discrete flow corresponding to this vector field on each of these edges. And because this is a convex combination, so that whatever value you get has to lie in this Newton polygon of this lattice. So it has these sort of bounded values. It takes values in this convex set. And the way that we yes.
N is a Newton polygon.
Mm-hmm.
And it's in R of whatever the dimension you are.
Yes, that's right. So you just take, for your lattice will have some finite collection of edges E1 up to ED, incident to each to every white vertex. And this N is just the convex hull of those edge directions. And so sort of a way that you can kind of think of what this dimer cover is that sort of at every white vertex in your graph, you're putting this SMV vector scaled. And so as you take this sort of scaling limit, you're sort of making smaller and smaller the spacing between these vectors, and they're somehow approximating some continuum vector field that's defined everywhere rather than just on a lattice. And so this is sort of, this kind of goes back to some previous work with Scott and Nishant, but basically in sort of a weak topology on these vector fields, if you look at this sort of scaling limit of what these discrete flows is, there'll be something that we call asymptotic flows, which just means that they're measurable vector fields that are also divergence-free and valued in this convex set, this Newton polytope, just because these original guys were valued there, and so in the limit they still are. So now to make our sort of limiting question is now sort of more precise, it's just the question is viewed as a random divergence-free vector field, what do these N dimer covers look like as you take the multiplicity and then the size of the graph to infinity? So I'll explain the answer to this question, and then I'll get to some more like concrete examples. But basically, you fix your continuum region. So you fix a region in RD, and you also fix a boundary condition. So that's just the boundary value of some divergence-free vector field. And you fix a sequence of regions approximating in the rescaled lattice, approximating your region and boundary condition. And you have this sort of large deviation principle. So you look at this is the multinomial dimer measure on this region. And in the iterated limit, as you take the multiplicity and then the size of the graph to infinity, these things satisfy a large deviation principle where the rate function is up to a constant given by just integrating a function, this surface tension function determined by the lattice. So this is sort of the completely analogous form to what's known for sort of standard dimers in 2 or 3 dimensions. And we also have explicit formulas for these an explicit description of this surface tension, which I will show you in the next slide. But sort of the second corollary of this is that there is sort of a limit shape story. So this is some functional, this is some convex functional, and it has a unique minimizer. And so when you have a unique minimizer and you have sort of a large deviation principle, what that says is that random samplers are going to concentrate at some exponential rate on that limit shape configuration. And so there will be some limit shape configuration which is given by just minimizing this over these allowed divergence-free flows. So one quick thing about this surface tension, and then I'll go to some examples of limit shapes. So how do we compute the surface tension? It's actually very analogous to the story for regular 2D dimers, which is that there's another quantity called the free energy, which is a function from RD to R, which is measuring sort of the growth rate of partition functions on the torus where you take periodic weights. So instead of taking all the weights to be 1, like in the theorem, we take all edges all edges parallel to E1 get some weight, E1 dot alpha, where alpha is some vector in RD. And it turns out that the free energy for this model has an incredibly simple formula. It's literally just log of the sum of these edge weights. And then what we show is that basically the surface tension is counting instead, the surface tension, which is a function on this Newton polytope, is instead counting sort of the number of dimer covers of the torus that approximate a particular, where the corresponding discrete flow approximates a particular constant slope. And so just like for regular dimers, what we show, but for any lattice lambda, is that the surface tension is just the Legendre dual of this free energy. And this free energy is just this totally simple log of a sum of exponentials. Yeah, so actually this should say, I'm sorry, this is a bad typo, but this should be e to the weight. So yeah, there's an exponential in there, e to the dot product. Okay, so this is sort of the complete story of the large deviation principle. Let me show you some actual examples. So there's more pictures. So first, let's just talk about Z2. So for Z2, and now you see the exponential here that should have been there on the previous slide. For Z2, the free energy is just this. So just to make things basically factor a little bit more nicely, I'm drawing Z2 in a slightly different way. So I'm drawing Z2 so that the edge directions are diagonal instead of straight. So it looks like this instead. And you can take the Legendre dual of this, and you get this also totally explicit function with logs. And here's some plots. So this is this one, the pointier, the one that's more convex looking. Why is the pointer no? This one is this is a graph of this function, and this is a graph of the analogous function, but for regular 2D dimers. So I should have put this formula on the slide, but for the regular 2D dimer version of this involves a sum of these sort of Lobachevsky functions, which are like log of integral of log of sine. So this function is drastically simpler and much more regular than sort of the analog for the 2D dimer model. So how about what's a limit shape actually look like? So the first example to try is the Aztec diamond. So first, as a comment on sort of what's the relationship between the limiting flow, divergence-free flow limit shape and a height function, it's simple. It's just that in 2 dimensions, in 2 dimensions, there's this fact that if you have a divergence-free thing, it's dual to something curl-free, and that duality just comes from rotating it. So this omega, which is divergence-free, is dual to the gradient of a function just by switching omega 1, omega 2 to minus omega 2, omega 1. So for the Aztec diamond, we can compute, and I'll explain in a minute, various ways to do this, what the limit shape height function is. And here it is. I showed it to you before, I guess. And here's the corresponding divergence-free flow. So it's just you take the gradient of this function and rotate it. And there's the graphs again. So let me explain some of the ways that you can actually compute these limit shapes now that we know they exist. So one way is to take the scaling limit of the critical edge weights. So we saw these earlier. These are the critical edge weights for each of these directions. So this is northeast and so on. And you can take the scaling limit of these things, and you will get the same divergence-free flow that I showed you on the previous slide. So this is one way to compute them if you have a closed form for the critical edge weights. So another way is that whenever you have one of these things where you have you're looking for the solution to an optimization problem of these forms, you can rewrite it in terms of Euler-Lagrange equations. And the Euler-Lagrange equation for a height function just looks like this. So you take it's a function of the gradient of the height function. You take the gradient of the surface tension and then the divergence. This equation is the solution to this equation is the limit shape. And so we have an explicit formula for the surface tension. So we can just write this PDE. So here's the PDE. It's almost like a Laplace equation, but you have these extra terms in the denominator that make it different. But it's pretty straightforward to check that this solves this PDE. So I don't know, I don't have a general solution to this PDE, but it's not hard to check once you have something that solves the PDE, that it does solve the PDE. And another method you can use that I won't give the formulas, but it's kind of a cool thing that Rick and Istvan worked out, is you can also describe these height function limit shapes as an envelope of kappa harmonically moving planes. So you're basically describing all of the tangent planes of the graph of the height function, and kappa is just a function of the surface tension. So since we know the surface tension, you can compute this kappa. So this is sort of, these are sort of, this in particular, so far I've sort of focused on 2 dimensions, and in particular this description of the Euler-Lagrange equation is specific to 2 dimensions. It's for the height function. So what is the sort of setup when you have something in more general dimension? Okay, that's strange. So in more general dimension, when we want to have the sort of Euler-Lagrange equations for the limit shape, we're going to write them in terms of the actual divergence-free flow omega. So when you have something divergence-free, what you can derive is the Euler-Lagrange equations are, well, first you just have the divergence-free condition, which I'm just including here. And then second, you have this family of D choose 2 equations, one for each pair of distinct indices of this form. So it's actually basically telling you that sigma of omega, or the gradient of sigma of omega is the gradient of a function, because you have this for all pairs of I and j. So I'll come back to this in a minute. But this is the form of these equations. And in 2 dimensions, what you can check is that you can derive the height function for the for the height function. Sorry, you can derive the Euler-Lagrange equation for the height function. There'll just be one equation here instead of, because D choose 2 is 1, and it will give you the PDE for the height function. So this is sort of a generalization of what these PDEs look like. So let me tell you about it. So these are the PDEs. Let me tell you about now a 3-dimensional example where we can compute a limit shape. So this is going to be in something called the body-centered cubic lattice. So this is a lattice in 3 dimensions, where first you start with a copy of Z3, and then you take the dual copy of Z3, so you put a vertex in the middle of every cube, and then you just connect nearest neighbors and you delete the original edges. So every vertex in this lattice has degree 8. And for this lattice, again, here's the free energy, and here's the surface tension. They have these very simple formulas. For Z3, just to say it, this free energy is also very simple. It's just a log of a sum of exponentials. And the surface tension is still its Legendre dual, but for whatever reason, it has a complicated formula. So these surface tensions are not always, they don't always look like just a sum of things with log in them. They can be more complicated. But the surface tension is, the free energy is always very simple. So okay, let me tell you about a region in this 3-dimensional lattice where we can actually compute the limit shape explicitly. So we call this like the Aztec cuboid, because it's a generalization of the Aztec diamond. And it's basically just a box in this BCC lattice, where it's an A by B by C box. And we require that A, B, and C satisfy this constraint, which just tells you that they're the same number of white and black vertices in this box. So if you think of the Aztec diamond sort of in this diagonal coordinate way, which I'm going to not draw very well. Then in this sort of diagonal coordinate picture, you have basically two squares, two rectangles. Thank you. All right, this picture was drawn too quickly. Maybe all right, that's not an Aztec diamond, maybe? It is. It is?
It is, the coloring is off.
Oh, okay.
Start with the last row, the last column of red.
Thank you. Okay, So there's red vertices, and then I'm not going to try to color the other vertices because maybe I'll do it wrong again. But you have, so what you can see is that, when you draw the Aztec diamond sort of on this diagonal version of Z2, so, if you did this construction in 2 dimensions to build the BCC lattice, you made this Z2 and this Z2, what you would just get is you would actually get Z2 back. You would just get Z2 rotated. And so in that picture, the Aztec diamond is just 2 rectangles overlaid on top of each other in this rotated Z2. And so this is sort of a generalization of the Aztec diamond in the sense that we sort of built the diagonal lattice, and then we looked at a box in the diagonal lattice. And on this box, like for the Aztec diamond, this is one of the other examples where it turns out that we can actually find an explicit formula for the critical, for the critical gauge in terms of binomial coefficients. And so we can compute this solution for finite graphs and take its scaling limit. And in the scaling limit, what you get, if you take, if you have to scale A, B, and C together in some consistent way, and what you get in the limit is a vector field, which is plotted here. And this vector field is divergence free, so it's plotted here for, I think, A is 1, and, alpha is 1, and beta and gamma are 2. And it turns out that this condition on the previous slide, this one here, this consistency condition, tells you that in the scaling limit, you have to choose alpha, beta, and gamma such that 1 over alpha is equal to 1 over beta plus 1 over gamma. So that condition tells you that this thing is actually also divergence free. So this is an example of a 3D limit shape for this model, and it's even smooth. So like the one for the Aztec diamond for this model, and unlike the Dimer model. So yeah, you can also write out explicitly what is this triple of Euler-Lagrange equations for the BCC lattice, and you can check that this guy solves the equations. And it's super easy to check that this solves the equations because, okay, omega 1 depends. Sorry, there's a coordinate switch here. This is an x, y, and z, and this is x1 is x, x2 is y, and x3 is z. But you only differentiate omega 1 with respect to the equivalent of y or the equivalent of z, but it doesn't depend on y or z. Okay, so I also said that one of the things that's a little bit funny and a little bit different about this model is that, okay, one of the questions, I'm starting with a 2D example, and I have to explain a little bit to make this picture make sense, but one of the things that's difficult is that it's a little bit hard to draw pictures of these 3D limit shapes. So I want to show you another way that you can kind of visualize these limit shapes that's also kind of special to this model. So this is made with the sort of Sinkhorn's algorithm. So let me explain. In regular dimers, if you looked at some discrete flow, right? You can always define a map where for every vertex, let's say I have my region, and I take a vertex in the graph, I could define some map where, for regular, where I just send, I send this vertex to the point in n of lambda, which is the, the slope at this point. So for regular dimers, you would just get a function that's very boring because it would always just send you to the corners. Because in regular dimers, you just get one edge with multiplicity 1, and the others are all unfilled. So it would just, you could define this map, but it wouldn't be very interesting because it would just be a map to the vertices of your polytope. But for the multinomial model, where we, as we take n to infinity, the value, we can have non-zero values on all the edges incident to this point, that they just have to sum to 1. And so the slopes, when you have this multinomial model, will actually be sent, you'll get non-trivial things where they're sent to points in this region. So this example is in a different lattice. This is if you take basically a big hexagon graph in the honeycomb lattice, which I'm maybe not going to draw the whole thing, with side length 30. and you numerically compute these critical gauge edge weights, which gives you a way to compute the slope of the sort of limiting discrete flow at every point, then you can embed it in the sort of polytope for the hexagonal lattice, which is this triangle. And so this is sort of a picture of this sort of discrete approximation of the multinomial limit shape. So you can I don't know, it's maybe hard to interpret this picture, but you can see that every face here of this graph does actually have 6 sides because every one of them is the image of a hexagon. And so we don't have an explicit formula for this thing, but we can compute it numerically, and you can see sort of some structure in this picture. And I'll show you also a 3D example from Z3. So you can take this sort of Aztec octahedron picture, which I showed way earlier. Maybe this was a mistake to go all the way back. Okay, maybe I'm not going to go all the way back. I showed at the very beginning a picture of a 3D dimer tiling of Z3 of the octahedron. And the sort of Newton polytope for Z3 is also the octahedron. And so you can also, so this is another numerically generated picture of, these are the images of the vertices under this map for that region, with n is 10, and these are the images of the edges. So I can show you a better version because, so one of the interesting things is that this map is actually not onto the new octahedron. So you can see that you get vertices on 4 out of the 8 faces. And there's kind of funny stuff where you see somehow that there are vertices that look like they're kind of clumping together here, like these 3. Another fact about this region, but it isn't true for all regions, is that the image of but this is just a symmetry thing, is the image of the black vertices and the image of the white vertices under this map are the same. And then you can also look at the edges where you just embed the image of the original edges of the graph. And this looks like kind of a tangled mess, but you can kind of see on some of these faces you have this sort of array of points, and it's sort of indented and sort of squished in on these other sides. So yeah, unfortunately it's still difficult to see 3D things in 2D even if they can move, but hopefully this still gives some sense of what these look like. And so these things, if you took n to infinity, would be a graph basically of the divergence-free flow limit shape. Okay, so 2 more things I just wanted to sort of comment on that we can kind of see, I don't know, where you can sort of see some additional structure in this model. So I mentioned that there's a way to rewrite the EulerLagrange equations in higher dimensions are kind of annoying. It's a whole family of equations instead of just one equation. And we haven't really connected back very well to the critical gauge functions that we saw in the discrete. So there is kind of an interesting connection. So there are these sort of dual EulerLagrange equations. So this seems to be one of these things that's very well known to people in PDEs, but not written down so frequently. But if you have you can turn this, the EulerLagrange equations for your divergence-free flow into a gradient variational problem. And so how does this work? Well, so we have 2 dual problems. So one of them is that we have some divergence-free flow that minimizes the surface tension integral. And then we have a dual flow which minimizes this free energy integral. Because these things are Legendre duals of each other, this thing minimizing this is equivalent to this thing minimizing this if they are related in this way. So these are both sigma and f are strictly convex. And that strict convexity means that their gradients are, and Legendre duality means that their gradients are inverses of each other and bijective. So alpha is uniquely determined by omega and vice versa with this definition. And so it turns out, and it's not so, it turns out that if you look at the EulerLagrange equations, that the sort of set of D choose 2 equations tells you that this dual guy alpha is the gradient of a function, which I'm calling capital H. And so then just the fact that omega is divergence free tells you that capital H satisfies this equation because gradient f of alpha is omega, and omega has to be divergence free. And so this is sort of a repackaging of the original EulerLagrange equations for the divergence-free flow into a gradient equation for this some kind of gauge field. And even in 2 dimensions, just to say, even in 2 dimensions, this is not the height function. So the height function we saw just comes from rotating omega. It is not as complicated. It's not applying the surface tension gradient to omega. So this is a different function that also exists in 2 dimensions, but it is much less. It's not as constrained as the height function. So the height function, for example, is Lipschitz, corresponding to the fact that these flows are valued in some bounded convex set. And this h, there's no bounds on the gradient of this h. The gradient of this h function actually does blow up in examples. On the other hand, somehow we sort of expect, though can't prove other than in 2 dimensions, that this gauge function actually should be smoother than the height function. Or, yeah, this gauge function should sort of be smoother than the height function, because it's just telling you, it's basically telling you how the, if I want this to be, it's basically telling you sort of how the local statistics or weights change as you move to different areas in your region. And so calling this the gauge equation, it is the gauge, and it also connects really well to the critical gauge functions that we actually have on the discrete, in the discrete. So here's the sort of simple form of the critical gauge equations, and I've added a parameter n because I'm just viewing these are the critical gauge equations for each graph Rn. And the theorem is that if capital H solves the gauge or Lagrange equation from the previous slide and is C1, which is a theorem in 2 dimensions and should be true in higher dimensions for this model, but not a theorem, then the scaling limit of the critical gauge functions for each finite graph are this limiting gauge function. So somehow this is where the critical gauge functions go in the scaling limit, is to this gauge function. So just to give a formula, here's the gauge function for the gauge function h for the Aztec diamond. There's more logs. Here's its graph. Its gradient does blow up as you go to the boundary, so it's really not Lipschitz. But yeah, you can. This is its formula, and you can check if you just take the as it should. This thing is the same as the limit shape flow we saw earlier. So these things all sort of determine each other, and they're all related to each other, but they have, you can find them in different ways. Okay, the last thing, which I'll say really quickly, that I just sort of think is an interesting phenomenon that kind of gives you a sense of how this model is a little different from the Dimer model, is the sort of regularity of the limit shapes. So for the standard Dimer model, limit shapes have these facets. So in these simple examples, the facets are just the regions where you see one color of Dimer. And what this corresponds to is that, it's places where the limit shape actually is valued on the boundary of the Newton polytope, or more generally at certain integer points, but that's for other phases that I'm not actually talking about here, that don't occur in the simple setup we have. And one of the things that you may have noticed is that on the Aztec diamond, or for the Aztec cuboid, the multinomial limit shapes we've seen don't have facets. They're just smooth. And it turns out that this is sort of a general, even though there's standard Dimer analogs would. And this turns out to be sort of a general phenomenon for this multinomial model. So, okay, we have to rule out some really unreasonable boundary conditions like this, where I force this Dimer is required to be included, this Dimer is required to be included. You can kind of like chisel out this region where there are a bunch of things required to be included, and then you have a free tiling. We're going to assume our regions do not have these regions that need to be chiseled out. And under that assumption, the multinomial these n to infinity multinomial limit shapes do not have facets. And this result does not depend on the dimension. This is true for the 3-dimensional lattices, any lattice to which our results apply. So any dimension D with this description with the edges. And in 2 dimensions, once you know there are no facets, you can just sort of use some classic elliptic regularity results to say that the 2-dimensional multinomial limit shapes are smooth. There's some technicalities with how how strong are and what kinds of convexity do you need to make these elliptic regularity results apply. And that's basically the challenge in moving this to higher dimensions, is finding the right, somehow in 2 dimensions, things where you have both this gauge function and the height function. That gives you enough structure that it's easy to just apply these elliptic regularity results. But in general, you'd need some sort of more ad hoc estimates to sort of bootstrap from this to this. And I don't know how to do that. But the reason you don't have facets is actually kind of a simple property of the surface tension that doesn't really need any integrability. Well, sort of needs integrability, but not in a direct way. And would apply to other models where there's a surface tension. So the key lemma is just that if you have some point in the boundary of your Newton polygon, I'll say that it has blow up if none of the directional derivatives from the interior exist. So any direction where I'm trying to go in this direction, I try to compute the gradient of sigma, it blows up. Those points are values that you cannot see in a limit shape in the interior. So for the so it turns out that for our model, and you can see this just by looking at the formula for the surface tension, that the entire boundary has this blow up property. And so you can never see the boundary in a limit shape. So for standard dimers, what you can find is that there's blow up if you go to any place on the edge, on an edge of the Newton polytope, you have blow up. But if you go toward a vertex, you do not have blow up. And so that's why in for example, these pictures, with all edge weights being 1, et cetera, you see regions where you have 1 color, or you see all colors, but you don't see regions where you have 2 colors. You can use more complicated weights and see regions where you have 2 colors, but that also changes your surface tension and so on. And so, but somehow, the set of slopes you're allowed to see from the boundary is sort of described by basically points where you can find some direction where the gradient of sigma exists going toward that point. All right, so thank you and happy birthday, Rick.
You showed us BCC for dimension 3 only. Is there any reason why only dimension 3 is?
No, there's no reason. You could do it in any dimension.
You mean it would work?
Yeah, it should work for. We haven't checked the critical gauge formulas, but I would really expect it to be very analogous, a very analogous formula with binomial coefficients. And you can construct it. You can construct higher dimensional analogs of the BCC lattice in the same way, where you take ZD and then the dual copy of ZD, and you connect.
But there's something special which happens in dimension 4, which is that the dual has distance 1 from the origin. But this doesn't matter.
I guess I haven't thought about it, but I wouldn't expect it to matter.
It works fine in all of it.
It works the same way.
It's not a function of the geometry, really. Just the common works that are
Yeah.
Okay. Thank you.
Another question?
Thank you for a very nice talk. So you were doing large deviations and Legendre transform. So I was wondering, does your model have good convexity property?
Yes, so it's strictly convex on the entire closed. So the surface tension is strictly convex on the entire closed Newton polytope. So it's actually more convex than the one for regular dimers, because the one for regular dimers is just constant and 0 on the boundary of the allowed. Sorry, this is a mistake. Yeah, so the regular dimer one, you can see it's like constant 0 on the boundary, so it's not strictly convex there, whereas this one is actually strictly convex everywhere. And the free energy is strictly convex, and it's also actually analytic and strictly convex on the whole plane instead of on some amoeba, some strict subset of the plane. So you have strict convexity and sort of stronger, in a stronger way than for the regular model.